far out in the western desert of Australia, a long way from any city light or highway noise. There is a patch of ground where 36 white dishes stand in loose formation, each one 12 meters across, all of them tilted toward the same quiet patch of sky. Nothing about the scene moves quickly. The dishes turn a few degrees over the course of an hour. The wind moves the spinifex grass around their bases, and somewhere inside a control room many kilometers away, the numbers those dishes are collecting scroll past on a screen. Slowly, the way tide comes in. This is a good place to begin, because it is a good place to think about what it actually means to listen to the universe, not to look at it in the way we usually mean that word, with light entering an eye or a camera lens. To listen to it the way you might listen for a familiar footstep in another room, or the particular hum of a refrigerator that tells you it is still working. Radio waves are a form of light too, just at wavelengths far longer than anything our eyes evolved to catch. And for most of human history, that entire part of the spectrum simply did not exist for us. Not because it wasn't there, because we had no ears for it. We have had those ears for less than 100 years now, and in that short stretch of time, a strange pattern has begun to repeat itself, over and over, in observatory after observatory, on continent after continent. Astronomers build a more sensitive instrument, point it at a familiar patch of sky, and find something that has apparently been sitting there the entire time, radiating quietly, waiting for someone to notice. Not a new event, an old one, freshly perceived, a signal that was already arriving patiently, for years or centuries or millions of years, before anyone built the machine capable of hearing it. This is a story about several of those signals, where they came from, how they were found, what they might mean, and what they still refuse to explain. It moves slowly and it wanders a little, the way a good, long conversation does, because the point isn't to race toward a single dramatic answer. Mostly, there isn't one yet. The point is simply to sit with what we've found so far, and to notice how strange and how large the picture is becoming. It helps to start with how we learned to listen at all for most of the history of astronomy. Looking at the sky meant exactly that. Light in the narrow visible band, gathered by an eye, then a lens, then a mirror. That changed in the early 1930s, almost by accident, at Bell Telephone Laboratories in New Jersey. An engineer named Carl Jansky had been given an unglamorous assignment: figure out what was causing a faint, persistent hiss of static that kept interfering with transatlantic radio telephone calls. Jansky built a rotating antenna, nicknamed the merry-go-round by his colleagues, mounted on wheels taken from a Model T Ford, so it could be turned slowly to track the source of the noise across the sky. Most of what he found was ordinary. Local thunderstorms produced one kind of static, distant thunderstorms produced another, but there was a third hiss, fainter and steadier than the rest, that rose and fell on a 23-hour and 56-minute cycle rather than a 24-hour one. That distinction mattered enormously. A 24-hour cycle would have pointed to something tied to the sun, and therefore to our own solar system. A cycle 4 minutes shorter than a full day is the signature of something fixed against the background of stars rather than the sun. What astronomers call a sidereal rhythm. Jansky eventually traced the source to the direction of the constellation Sagittarius, toward the center of our own galaxy. He had accidentally discovered that the Milky Way itself was broadcasting in radio waves, and had built, without setting out to, the first radio telescope. He published his results in 1933. The New York Times covered it. And then, remarkably, almost nobody in professional astronomy followed up. The person who did was not an astronomer at all, but a radio engineer named Grote Reber, working from his mother's backyard in Wheaton, Illinois. In 1937, using his own money and his own labor, Reber built a 9-meter parabolic dish by hand in his spare time, becoming for a while the only person on the planet actively practicing radio astronomy. He produced the first crude radio maps of the sky, confirming and extending Jansky's discovery, publishing his results in mainstream astronomical journals despite having no university affiliation. For close to a decade, the entire field of radio astronomy consisted, essentially, of one dish in one backyard. What changed its fortunes was the Second World War, and specifically radar. The urgent wartime need to detect aircraft and ships by radio reflection drove enormous advances in antenna design, receiver sensitivity, and signal processing, along with a large supply of trained engineers and surplus equipment once the war ended. In the decade that followed, radio astronomy expanded rapidly in Britain, in the Netherlands, and in Australia, where the vast, radio-quiet interior of the continent turned out to be an extraordinary natural asset. Facilities like the Parkes Observatory in New South Wales, completed in the early 1960s, became central players in a field that was now uncovering one unexpected class of object after another: quasars, blazing centers of distant galaxies once mistaken for nearby stars, the sea of ancient light called the cosmic microwave background, discovered by accident in 1965, and, in 1967, the pulsar, whose story we will come back to later, because it turns out to matter quite a bit for signals discovered decades afterward by the 21st century. The tools available to radio astronomers had grown almost unrecognizably capable, and nowhere more so than in Western Australia, where two purpose-built instruments were constructed within a few hundred kilometers of each other, in one of the most radio-silent regions left on the planet, the Murchison Wide Field Array, a dense forest of simple dipole antennas tuned to low frequencies, and the Australian Square Kilometre Array Pathfinder, generally known by its acronym, ASCA. It is a SCAP that concerns us. First ASK app consists of those 36 dishes described a moment ago, each fitted with a specialized receiver called a phased array feed, a technology that lets a single dish observe many separate patches of sky simultaneously rather than just one. The practical effect is an enormous field of view, roughly 30 square degrees in a single pointing, an area of sky equivalent to about 150 full moons placed side by side. No previous radio telescope had been able to survey so much sky so quickly while remaining sensitive to faint, extended structures that earlier, narrower instruments would have simply missed entirely. Starting in the late 20s, ASCAP began feeding data into an ambitious project called the Evolutionary Map of the Universe, usually shortened to EMU. The plan was straightforward to state and staggering in scale. Catalog radio sources across nearly the entire southern sky, aiming to increase the total number of known radio sources from around 2.5 million, the accumulated total of every radio survey in the history of the discipline, to something closer to 70 million. In a single, coordinated effort, that is the kind of number that is difficult to hold in your head, so it might help to picture it differently. Imagine every radio source ever catalogued by every telescope built since Jansky's rotating antenna in the 1930s, laid out as a single, carefully assembled catalogue. Now imagine a project designed to produce something roughly 30 times larger than that entire accumulated record, not over another century, but within a handful of years. That was the ambition behind EMU. And processing a dataset of that size meant, inevitably, that a great deal of it would first pass in front of human eyes. Because even now, with considerable help from automated detection software, there is no substitute for a trained astronomer simply looking at an image and noticing that something in it does not fit. In September of 2019, an astronomer named Anna Kopinska was doing exactly that, scrolling through early images from the EMU pilot survey, checking the raw radio maps by eye, the same slow, unglamorous, essential task that has preceded a large fraction of the major discoveries in the history of the field. Not photographs, not anything a person would immediately recognize as an image in the ordinary sense. These were full-color maps of radio brightness across the sky, the electromagnetic equivalent of a temperature map, showing where faint radio energy was arriving from and how strong it was. Something in one of those maps caught her attention, a shape that did not match anything in her mental catalogue of known radio sources, galaxies, star-forming regions, the lobes of active galactic nuclei, supernova remnants. None of it. What she was looking at was a ring, faint, nearly perfectly circular, and enormous, hanging in the radio data like a smoke ring with no fire visible anywhere near it. There was no matching object at any other wavelength, no trace in visible light, no trace in infrared, no trace in X, just a pale circle of radio emission, sitting quietly in deep space, apparently unconnected to anything. Kopinska did what astronomers confronted with a genuine anomaly have done for as long as there have been astronomers. Confronted with anomalies, she flagged it and moved on, uncertain what else to do with it in the moment. The label she attached to the image, according to the story that circulated afterward among her colleagues, was 2 letters and a question mark, not a formal designation. Just an honest, unguarded reaction to something she had never seen before and could not immediately place within days. A colleague on the project found a second one in a different part of the sky. Then a third turned up. Then a fourth was located by searching back through archival data from an older telescope in India. Data that had been sitting untouched since 2013. The ring hiding in plain sight in a dataset nobody had thought to look at quite that way. These were not instrumental glitches or processing artifacts. They were confirmed independently at multiple radio frequencies by multiple facilities. They were real. The scientist leading the EMU project, Ray Norris of Western Sydney University, had in fact predicted years earlier that a survey instrument as sensitive and wide-fielded as a SCAP would eventually turn up phenomena that existing theory simply had no box to put them in. He had even given this category of anticipated surprise an informal name in advance. Only half seriously. He called them, cheerfully, the WTFs. He had not expected to find one quite this quickly, and he had certainly not expected it to look like a ring 20 times the width of the entire Milky Way. Norris and his collaborators eventually gave the objects a formal, deliberately understated name, odd radio circles, or ORCs for short. A label chosen partly because odd was, if anything, an understatement for something so large and so thoroughly unexplained. As of the most recent survey work, somewhere around 8 of these objects have been confirmed, with a further handful of candidates still under investigation, each one a ring of what is called synchrotron radiation, the particular kind of light produced when electrons are accelerated to velocities close to the speed of light within a magnetic field and spiral along the field lines, shedding energy as they go. It is the same basic emission process that lights up supernova remnants and the jets streaming from black holes, just organized here into a shape nobody had catalogued before, a ring, brighter at its outer edge than in its interior, the way a soap bubble catches more light along its rim than through its center. The scale involved is genuinely difficult to internalize. The confirmed ORCs range in estimated diameter from several 100,000 light-years up past 2 million light-years across our own galaxy, home to something like 200 billion stars and roughly 100,000 light-years in diameter, could be set down inside a single one of these rings more than 20 times over and still leave room around the edges. These structures rank among the largest individual objects that astronomers have ever identified in the observable universe. And until 2019, not one of them had ever been noticed. The research team's first task, once they were confident the objects were real, was working out what an OR-C is not. Because ruling things out narrows the field considerably. They are not supernova remnants. Those are typically only a few dozen light-years across, embedded close to the flat disk of their host galaxy. Off by a factor of roughly 10,000 from the scale of an OR, they are not planetary nebulae, the glowing shells shed by dying sun-like stars, which are smaller still. They are not the familiar radio lobes produced by jets from a supermassive black hole at a galaxy's center, because those lobes are elongated and asymmetric, stretched out along the jet's axis, while OR-Cs are close to perfect circles. And they are not Einstein rings, the gravitational lensing effect in which the light from one distant object is bent by the gravity of a massive foreground object into a ring shape, because that phenomenon requires a very specific alignment with a massive lensing body sitting directly along the line of sight. And no such foreground object has been found at the center of any confirmed OR-C. What the researchers did find at the geometric center of several of the confirmed rings was something else entirely, a galaxy. Specifically, in a handful of the clearest cases, a massive elliptical galaxy sitting almost exactly at the center of the ring, as precisely centered as a bullseye. The odds of that being coincidence, a galaxy randomly happening to land at the exact midpoint of a structure 2 million light-years wide, are vanishingly small. Whatever is producing these rings, the evidence strongly suggests it originates in that central galaxy from there. 3 broad explanations have been proposed, and it's worth walking through all 3, because none of them has been ruled out and none has been confirmed, which is itself part of the story. The first involves the merger of 2 supermassive black holes. When 2 galaxies collide and their central black holes eventually spiral together and merge, the event can release an extraordinary pulse of energy outward into the surrounding intergalactic gas, in principle producing an expanding spherical shock wave that, viewed from far away after billions of years of expansion, could appear to us as a ring. The second explanation involves what's called a starburst termination shock, a scenario in which the central galaxy experienced an intense, relatively brief period of star formation, and the combined stellar winds from millions of young stars, reinforced by the supernova explosions of the most massive and short-lived among them, drove a shock wave outward through the surrounding gas over hundreds of millions of years, eventually reaching the enormous scale now observed and exciting electrons along its leading edge into the synchrotron glow we detect. The third explanation is comparatively simple to state, though harder to confirm, that we may simply be looking straight down the barrel of an ordinary radio jet from an active galactic nucleus, so that its 2 lobes, which would normally appear as an elongated double structure, overlap from our particular viewing angle and read as a single ring. It requires an unusually precise alignment, but the universe is large, and unlikely alignments do eventually occur. Somewhere none of the 3 hypotheses has been eliminated by the data collected so far. None is clearly favored over the others. What the evidence does establish, fairly confidently, is that something happened in those central galaxies, something energetic enough and violent enough to sculpt a structure of glowing plasma larger than any galaxy it surrounds, an event whose light is only now reaching us, its origin billions of years in the past, its cause still argued over in journal articles and conference talks, and the odd radio circles turned out to be only the first entry in a much longer list. Before going further with the newer signals, it's worth pausing on an older story, because it set the pattern that so much of what follows would end up repeating, and because one of its central ideas, something astronomers now call the death line, will matter quite a bit later. In 19, a graduate student at the University of Cambridge named Jocelyn Bell was operating a radio telescope she had helped build with her own hands. A sprawling array of wires and posts covering an area equivalent to about 57 tennis courts, designed to study a class of object called quasars by watching how their radio signals twinkled or scintillated as they passed through the solar wind. It was, by her own later description, unglamorous work. Her job was to feed nearly 130 meters of chart paper through the telescope's pen recorders every 4 days and then examine it by hand. Looking for the twinkling signature the project was built to detect in August of that year. Buried in the paper, she noticed something she described afterward as a bit of scruff, a faint, unfamiliar smudge that didn't look like scintillation and didn't look like ordinary interference either. It reappeared in the same part of the sky roughly 4 minutes earlier each day, the sidereal signature. The same tell that had led Karl Jansky to the center of the galaxy 3 decades earlier, indicating a genuine celestial origin rather than anything terrestrial. It took her about 3 months of watching to catch it again in a form clear enough to study properly, because the source didn't reappear on every pass. When a faster chart recording finally captured it well. In late November, what emerged was startling. A train of pulses, arriving with almost unnerving regularity, once every 1 1/3 seconds. Each pulse only a few hundredths of a second wide. The precision was the strange part. Natural astrophysical processes, as far as anyone understood them at the time, simply did not produce anything that regular. Bell and her supervisor, Anthony Hewish, only half-jokingly nicknamed the source Little Green Man 1, entertaining, briefly and not entirely seriously, the possibility that they had detected some kind of artificial beacon. Bell herself grew skeptical of that idea fairly quickly, mostly because within weeks she located 3 more sources doing exactly the same thing in completely different parts of the sky, each with its own distinct period. It seemed unlikely that for separate alien civilizations would all choose to announce themselves in the same unusual manner, on the same night sky, to the same graduate student. The real explanation, worked out over the following months by Hewish, Bell and colleagues, was in its own way just as strange as an artificial beacon would have been. The source was a neutron star, the collapsed core left behind after a massive star explodes as a supernova, a stellar remnant so dense that a teaspoon of its material would weigh roughly as much as a mountain, packing more mass than our own sun into a sphere only about 20 kilometers across. Such an object, if it happens to be spinning rapidly and possesses a powerful magnetic field misaligned with its rotation axis, will sweep a beam of radio emission around the sky like a lighthouse. If that beam happens to cross the Earth once per rotation, a radio telescope will register it as a precise, repeating pulse, a rhythm dictated not by intelligence, but by the simple, relentless mechanics of a dead star spinning in place. Bell and Hewish had discovered the first pulsar, an entirely new category of astronomical object that nobody had previously observed. Hiding in data that had originally been collected to study something else altogether, the discovery earned the Nobel Prize in Physics in 1974, awarded to Hewish and to the radio astronomer Martin Ryle for their contributions to the development of radio astrophysics broadly. It was awarded to Hewish and not to Bell Burnell herself, a decision that remains debated among historians of science to this day, given that it was her patient. Hands-on examination of the chart paper that produced the discovery in the first place. What matters for our purposes is less the controversy and more the pattern it established, one that would recur again and again over the following decades, a new instrument, built for one purpose, reveals something entirely unanticipated, and the discovery is made not by a machine, but by a person looking closely and noticing that something doesn't fit the expected picture. It also matters because pulsars, once studied in detail, revealed a boundary in their own behavior that astronomers refer to as the death line. Here is the basic idea. A pulsar's radio beam is powered by the extreme electric fields generated near its magnetic poles, fields strong enough to rip charged particles directly from the star's surface and accelerate them to speeds close to the speed of light. Those accelerated particles then radiate gamma rays, which in turn produce cascades of new particle pairs, a chain reaction that ultimately generates the coherent radio beam we detect from Earth. But that whole cascade requires a particular combination of rapid rotation and strong magnetic field. As a pulsar ages, it gradually loses rotational energy and slows down, and as it slows, the electric fields near its magnetic poles weaken below a certain combination of spin rate and magnetic field strength. Calculated from the physics of the particle cascade itself, the mechanism simply stops working. The pulsar, still spinning, still magnetized, effectively runs out of the specific conditions needed to broadcast, and falls silent in radio. That boundary in the mathematics is the death line, and for decades it was treated as one of the more solid, reliable predictions in pulsar physics. Cross it, and a neutron star should have nothing left to say. We will need that idea again before this is over. But first, a signal from much closer to home, and a mystery that took 20 years just to get a namemate, 100 light-years from Earth, close by galactic standards, near enough that its light left home around the time the pyramids at Giza were already ancient. There is a dead star that spent 20 years being simultaneously one of the brightest objects in the sky and completely invisible. The story starts in 1972 with a small NASA satellite called SAT, the second in a program of small astronomy satellites designed to survey the sky in gamma rays, the highest energy form of light in the entire electromagnetic spectrum. Gamma rays are produced by the most violent processes the universe has to offer: supernova explosions, matter spiraling into black holes, particles slamming into one another at velocities close to the speed of light. They are, in a sense, the fingerprints left behind by cosmic violence, and SAS-2 had been built to map where those fingerprints were coming from, scanning the sky. The satellite picked up an intense, steady source of gamma radiation coming from the direction of the constellation Gemini. It was bright. It stayed bright, observation after observation, and it had no obvious counterpart at any other wavelength, no matching object in visible light, no radio source, no infrared glow. Whatever was producing all that gamma radiation appeared to be broadcasting loudly on one channel while remaining completely silent on every other, as though something enormously powerful were hiding in plain sight. Part of the trouble was resolution. SAS-2's gamma-ray optics could narrow the source down only to a patch of sky a few degrees wide, an area still crowded with thousands of ordinary stars and several other known objects, any of which might, in principle, have been the culprit. Pinning down the actual source with the technology of the early 1970s was simply not possible. The Italian physicist Giovanni Bignami, who would go on to spend the better part of 2 decades chasing this particular mystery, gave the unidentified source a name that was, in its own quiet way, a joke: Gemini, a contraction of Gemini gamma-ray source, which also happens to mean, in Bignami's native Milanese dialect, something close to it isn't there. For 20 years, that name fit uncomfortably well. Gemini sat near the top of the list of brightest persistent gamma-ray sources in the entire sky, outshone at that wavelength only by the well-known Villa pulsar, with something like 99% of its total detected energy output arriving in gamma rays alone. And yet every attempt to pin it down at any other wavelength came back empty. Radio telescopes searched and found nothing. Optical telescopes searched and found nothing. The source was, by every available measurement, simultaneously there and not there, an object announcing itself unmistakably in one part of the spectrum, while giving every telescope, tuned to any other part of the spectrum, absolutely nothing to work with. The first real crack in the puzzle came in 1983, when Bignami's team used NASA's Einstein X-ray satellite to pick up a faint X-ray signal from roughly the right direction. It wasn't strong enough to pinpoint the source precisely, but it narrowed the search considerably. Then came another long wait, roughly 8 more years of instruments being designed, launched, and pointed patiently at the same small patch of sky, until, in March of 1991, 2 separate missions arrived at an answer within weeks of each other. The German-built Rosat X-ray Observatory, sensitive enough to pick individual sources out of a crowded field, detected a signal from Geminga's location that pulsed, rising and falling with a period of 0.237 seconds, a little over 4 times a second, with the steadiness of a metronome. Within weeks, the American Egret instrument aboard the Compton Gamma Ray Observatory confirmed the exact same rhythm in gamma rays. The X-ray pulses and the gamma ray pulses were ticking in perfect synchrony that settled it. Geminga was a pulsar, the same basic category of object Jocelyn Bell had discovered by ear, so to speak, 24 years earlier. A spinning neutron star left behind by a supernova that had detonated roughly 300,000 years earlier, now rotating on its axis more than 4 times every second, sweeping beams of radiation across space like a lighthouse built from the corpse of a star. But Geminga was and remains a strange member of even that unusual family. Its first oddity was exactly the one that had kept it hidden for 2 decades. It produced essentially no detectable radio pulses at all, at a time when every previously known pulsar had been found precisely because it did emit in radio. It took until 1997, using the Pushino Radio Astronomy Observatory in Russia, for astronomers to finally detect extremely faint radio pulses from Geminga, and when they found them, the reason for 2 decades of failure became clear. The pulses were arriving at a frequency of roughly 100 MHz, well below the 430 to 1600 MHz range that essentially every standard pulsar survey up to that point had been built to search. Geminga had never actually been silent. It had been broadcasting for 300,000 years. Astronomers simply hadn't been listening on the right channel. The second oddity involved motion. Using observations from telescopes in Chile and Hawaii, Bignami's team found that Geminga was sweeping across the sky at an unusually rapid clip for something so far away, on the order of 0.2 of an arcsecond per year, at a distance of 800 light years. That translates into an actual velocity of roughly 210 kilometers per second, a dead star, containing about 1.5 times the mass of our Sun, compressed into a sphere some 20 kilometers across, hurtling through the galaxy at somewhere near 750,000 kilometers an hour. That is, in astronomical terms, sprinting. The third oddity, revealed in 2003 by a team led by the astrophysicist Patrizia Caravio using the European Space Agency's XMM Newton X-ray Observatory, was visual in an eerie sort of way. 2 long, glowing tails of X-ray emission trailing behind Geminga as it raced through the galaxy, together stretching some 3 trillion kilometers across the sky, like the wake behind a fast-moving ship. As Geminga plows forward through the thin gas and magnetic fields of interstellar space, it compresses the material ahead of it into a bow shock, and behind that shock, Electrons and their antimatter counterparts, get swept up and accelerated along the enhanced magnetic field lines, radiating X-rays as they spiral outward. The result is a pair of luminous contrails marking the star's path, visible only to X-ray telescopes. Utterly invisible to the eye, but the most significant chapter in Geminga's story had nothing to do with its structure, its motion, or its tails. It concerned what the star had apparently been doing, quietly, to every living thing on Earth. For roughly 300,000 years, the thread starts a little earlier than Geminga's own story, with a satellite called Pamela, an Italian-led mission launched in 2006 to study cosmic rays, the high-energy particles constantly raining down on Earth from deep space. Among the particles Pamela was built to count were positrons, the antimatter twin of the ordinary electron. Positrons are expected in the cosmic ray flux. They're produced routinely by collisions between ordinary cosmic ray particles and interstellar gas. What Pamela found, when its results began to be published a few years into the mission, was more positrons than that ordinary background process could account for, particularly at higher energies. An excess that immediately caught the attention of particle physicists for a very specific reason. One of the predicted signatures of dark matter, the invisible substance thought to make up roughly 5/6 of all matter in the universe, is that pairs of dark matter particles might occasionally collide and annihilate each other, producing exactly this kind of electron-positron excess as a byproduct. The stakes, if that explanation held up, would have been difficult to overstate. The first direct detection of the effects of dark matter particles, a result that would reshape a significant portion of modern physics. So when an even more capable instrument, the alpha magnetic spectrometer, a state-of-the-art particle detector bolted to the outside of the International Space Station, roughly 400 kilometers above the Earth's surface, was switched on in 2011. One of its central goals was measuring that positron excess with far greater precision than Pamela had been able to achieve. By 2013, the alpha magnetic spectrometer had recorded upward of 400,000 positron events, the largest sample of cosmic ray positron data ever assembled at that point, and it confirmed, with much tighter statistics, that the excess Pamela had first flagged was real, and that it extended up to quite high energies for several years. The dark matter explanation remained a live and exciting possibility, but the answer, when it started to come into focus, pointed somewhere else, not toward exotic invisible particles annihilating each other in deep space, but toward the ordinary, if extreme, physics of spinning dead stars, and specifically toward the ghost hiding in the constellation Gemini in 2017. An observatory called HAWC, the High Altitude Walter-Cherenkov Observatory, sited at high elevation near Puebla, Mexico, specifically to catch the faint atmospheric showers produced by extremely energetic gamma rays, detected something new around Geminga, a halo, a diffuse cloud of gamma radiation surrounding the pulsar, with individual photon energies between 5 and 40 trillion electron volts, energies trillions of times greater than a photon of visible light. The mechanism producing it was inverse Compton scattering, electrons and positrons, accelerated to extreme energies by Geminga's spinning magnetic field, colliding with the faint background of starlight that fills interstellar space and boosting individual photons of that ordinary light all the way up into the gamma ray range-den. In 2019, a team led by the astrophysicist Mattia Di Mauro used roughly a decade's worth of accumulated data from NASA's Fermi Gamma Ray Space Telescope to map that halo in full. It was not small. At an energy of about 10 billion electron volts, the halo spanned some 20 degrees of sky, an area comparable to the Big Dipper. At lower energies, it grew even larger. If human eyes could perceive gamma rays directly, Geminga's halo would be one of the most conspicuous features of the night sky, spanning an area roughly 40 times the size of the full moon. De Morrow's team went further, calculating that Geminga alone could plausibly account for as much as 20% of the total high-energy positron excess, measured by the alpha magnetic spectrometer. Extrapolating that contribution across the full population of similar pulsars scattered through the galaxy, the most likely explanation for the entire anomaly stopped being exotic dark matter, annihilation, and became something considerably more mundane. In the sense that mundane can mean a spinning dead star flinging antimatter across interstellar space, ordinary. If extreme, pulsar physics, repeated across enough dying stars to add up to a measurable signal at Earth, which leaves us with a reasonably strange picture to sit with for a moment. A single neutron star, roughly 20 kilometers across, 800 light-years from Earth, has been showering our planet and everything on it, with a steady rain of antimatter particles for around 300,000 years, alongside a gamma-ray halo 40 times the apparent size of the full moon, both completely invisible to us until we happened to build the right combination of satellites, high-altitude water tanks, and orbital particle detectors to notice. Not one instrument, a sequence of them, spread across nearly 50 years, each closing a little more of the gap between what was actually happening in the sky above us and what we were capable of perceiving. Geminga's radio silence was never really silence. It was a mismatch between the frequency it was broadcasting on and the frequencies our telescopes happened to be tuned to listen for. Its positron rain was never a new phenomenon that started when we launched a particle detector into orbit. It had been arriving, continuously, since long before human beings existed as a species. The instruments changed. The sky did not. And by the time the third strange signal in this story came along, arriving not from a single identifiable object, but from apparently random locations, scattered across the entire observable universe, astronomers were about to discover that 800 light-years and 300,000 years were, in the scheme of things, rather modest numbers to be dealing with in 2001. The Parkes Radio Telescope in New South Wales was carrying out a routine survey near the small Magellanic Cloud, one of the small satellite galaxies orbiting our own, searching methodically for somewhere in that survey, in among roughly 480 hours of recorded sky, the telescope registered a single brief pulse of radio energy. Nobody noticed at the time. The data was archived, stored on tape and then on disk, and left alone for 6 years, one recording among many thousands. Waiting in 2007, a professor at West Virginia University named Duncan Lorimer set an undergraduate student, David Narkovic, to work combing back through that old archive. Not for pulsars this time, but specifically for bright, isolated, one-off pulses, the kind of signal the standard pulsar search algorithms would have automatically filtered out, since those algorithms were built to find things that repeat, not things that flash once and vanish. It was, in essence, a search for needles that had already been thrown away along with the haystack. Narkovic found one anyway was a single burst, under 5 milliseconds long, so intensely bright that it saturated the telescope's receiver in its primary beam, registering a peak flux of around 30 Janskis, a unit of radio brightness. For context, the great majority of astronomical radio sources register at 1,000th of that value or smaller. This one burst was tens of thousands of times brighter than a typical background source, flaring, peaking, and disappearing again in less time than it takes a hummingbird to complete a single wing beat. What made the signal identifiable as something more than local interference was its shape, specifically a property called dispersion. As radio waves travel through ionized gas, the free electrons in that gas slow the lower frequency components of the signal slightly more than the higher frequency ones, so that, over a long enough journey, the higher frequencies arrive at a telescope a little earlier than the lower ones, an effect that accumulates the further the signal travels and the more ionized material it passes through along the way. By measuring exactly how much that delay was, astronomers can estimate how much ionized material a given signal has traveled through, and the dispersion measured in this particular burst was far too large to be explained by gas within our own galaxy alone. The signal had crossed the intergalactic medium, the sparse material lying in the vast spaces between galaxies. It had come from outside the Milky Way. Lorimer's team calculated a likely distance somewhere in the range of 1.5 to 3 billion light-years, meaning the pulse had been traveling through empty space for longer than complex life has existed on Earth before it happened to strike a radio dish in rural Australia during a routine survey, sit unnoticed in an archive for 6 years, and then finally be recognized by a student combing back through old data. The energy implied by that distance was almost absurd. In under 5 milliseconds, whatever produced this burst released, in radio waves alone, roughly as much energy as our sun radiates across its entire spectrum over several days. Not its whole electromagnetic output over that time, just its radio output in an instant, which meant that whatever mechanism was responsible had converted energy into coherent radio, a mission with an efficiency that had no real precedent in the observational record up to that point. The event, which came to be known as the Lorimer burst, was estimated to be somewhere around 10 to 12 orders of magnitude brighter than any previously known radio pulse. It did not fit the profile of a pulsar. It did not fit any previously catalogued category of transient signal. It was, by every available measure, something new, and then, for a while, not much happened. The wider astronomical community was, understandably, cautious. A single event, recorded by a single telescope, found years after the fact in archival data, with no way to go back and confirm it with a second observation, is not the kind of evidence that new physics is usually built on. Worse, in 2010, a researcher at Swinburne University named Sarah Burr, digging through the same body of Parkes data, found a batch of additional signals that superficially resembled the Lorimer burst, but turned out, on closer inspection, to be something considerably less exotic: interference from the observatory's own on-site microwave ovens. Staff had apparently been opening the oven doors before the heating cycle finished, and the escaping radiation, picked up by the telescope's sensitive receivers, produced dispersed pulses on the recording that closely mimicked the profile of a genuine astrophysical burst. These imposter signals were given the name peritons, and their existence cast a real shadow over the credibility of the Lorimer burst itself. If a kitchen appliance could fake a cosmic signal well enough to fool careful researchers for years, how confident could anyone really be that the original burst was not some similar, still unidentified artifact of the instrument or its surroundings? The resolution came in 2013, when Dan Thornton, a postgraduate student at the University of Manchester, working through the same Parkes archive with a fresh eye, found 4 additional bursts, all showing the same telltale dispersion signature, all detected at high galactic latitudes, far from the crowded plane of the Milky Way, all with dispersion measures too large to be explained by gas within our own galaxy. Some were dispersed almost 3 times more heavily than the original Lorimer burst, implying distances on the order of 5 to 10 billion light-years. Thornton's team gave the phenomenon the name that has stuck ever since: fast radio bursts, or FRBs. Crucially, these 4 new bursts had been detected with a receiver system physically incapable of picking up microwave-on interference, the way the Periton events had. which effectively ruled out that particular explanation and put the reality of the phenomenon on considerably firmer ground. From that point forward, the field expanded rapidly, becoming, within a decade, one of the fastest growing areas of research in all of observational astrophysics, says of the most recent surveys. Several thousand fast radio bursts have now been catalogued, arriving from apparently random locations scattered across the sky. Individual bursts last anywhere from a fraction of a millisecond to a few milliseconds, and the estimated overall rate, extrapolated from what current telescopes actually manage to catch, runs to something on the order of 1,000 or more such bursts occurring somewhere across the whole sky every single day. Dozens of individual sources have now been traced back to specific host galaxies, some of them billions of light-years distant, and after nearly 2 decades of sustained study, involving hundreds of research groups on every inhabited continent, using some of the most sensitive radio instruments ever constructed, the central question of exactly what produces the majority of these bursts remains genuinely, formally unresolved. That said, the basic physics of the bursts does constrain the possibilities considerably, and it's worth walking through the logic, because it's a good example of how astronomers can pin down an object's properties without ever seeing it directly. The brevity of a burst limits the physical size of whatever is producing it. Light travels roughly 300 kilometers in a millisecond, and if an emitting region is much larger than the duration of its own pulse would suggest, light from different parts of that region would arrive at slightly different times, smearing the signal out over a longer stretch than what's actually observed. A pulse lasting close to a millisecond therefore implies a source no larger than a few hundred kilometers across, an object smaller than many mid-sized asteroids, somehow generating the single most energetic burst of coherent radio emission ever measured. The coherence itself is the second constraint, the fact that a burst arrives as a single sharp, well-defined spike rather than a diffuse smear of radio. Noise means that the entire emitting region must be firing in near-perfect unison. The way the light in a laser beam is organized and synchronized rather than random and diffuse. The way the light from a hot, glowing object is not. Ordinary thermal radiation, the kind given off by hot gas or a stellar surface, simply cannot reach the brightness implied by these bursts, and the numbers involved make that clear on their own. The brightness temperature of a typical fast radio burst, the temperature an ordinary thermal source would need to reach in order to produce the same intensity of radiation, works out to something on the order of 10 to the power of 35 Kelvin. That number describes no real temperature anywhere in the universe. It functions instead as a kind of mathematical red flag, a sign that the emission cannot possibly be thermal in origin and must instead be coherent, produced by some mechanism capable of organizing enormous numbers of electrons to radiate in near-perfect lockstep. There is essentially one known category of astrophysical object compact enough, energetic enough, and magnetically extreme enough to plausibly satisfy both constraints at once. A magnetar is a neutron star whose magnetic field is so intense that it distorts the basic structure of the star itself. An ordinary neutron star already carries a magnetic field roughly 1 trillion times stronger than Earth's own. A magnetar's field is roughly 1,000 times stronger even than that, on the order of 1,000,000,000,000 times the strength of the field generated by the planet you happen to be standing on. At a magnetar's surface, that field is powerful enough to distort the shape of individual atoms, stretching them into narrow cylinders aligned with the magnetic field lines, and to alter the way light itself propagates nearby, splitting photons into different polarization states and bending their paths. The field also stores enormous amounts of energy in twisted configurations that can, from time to time, release that energy suddenly and violently. In events called starquakes, when the crust of the neutron star cracks under the accumulated magnetic stress and the field, lines snap into a new configuration, unleashing a burst of radiation detectable, in principle, from clear across the observable universe. The connection between magnetars and fast radio bursts moved from an educated guess to an observed fact on the 28th of April, 2020, when two independent instruments, the CHIME telescope in Canada and a much simpler, purpose-built array in the United States called STARE-2, simultaneously detected a bright radio burst arriving from the direction of a known galactic magnetar, catalogued as SGR 1935 plus 2154, located roughly 30,000 light-years away in the constellation Vulpec. The radio pulse arrived at the same moment as a burst of X-rays picked up independently by orbiting satellites, and it carried the same dispersed, spectrally broad signature characteristic of an extragalactic fast radio burst. Except this time, the source was a magnetar already well known to astronomers, sitting inside our own galaxy. It was, technically, the very first fast radio burst ever detected originating from within the Milky Way, and it settled, about as conclusively as such things get settled, that magnetars are indeed capable of producing fast radio burst-like emission, but it also introduced a complication that has kept the field from calling the mystery closed. The burst from that particular magnetar, while bright by the standards of galactic events, was roughly 1,000 times fainter than even the weakest fast radio bursts detected coming from other galaxies. Had an identical event occurred 1 billion light-years away instead of 30,000, no telescope currently operating would have been sensitive enough to detect it at all. So while the observation firmly established that magnetars can produce burst-like radio emission, it left open, and arguably sharpened, the question of what could possibly account for the much more luminous events routinely detected from far outside our galaxy, either a considerably more extreme magnetar than any yet observed close to home, or some additional mechanism that amplifies the burst energy well beyond what a single starquake seems able to provide, or, possibly, a genuinely different physical process altogether operating alongside the magnetar channel. Then there are the repeaters. The great majority of catalogued fast radio bursts appear, so far as current observations can tell, to be one-off events, a single burst from a single location, never repeated in all the years telescopes have kept watching that spot, but a modest fraction of sources, on the order of 4% of those catalogued so far, have been observed to burst more than once, sometimes many times over, and these repeating sources behave noticeably differently from the apparent one-offs. Their individual bursts tend to be broader in frequency, more structurally complex, and more variable in duration. The very first repeating source ever identified was found using the Arecibo Observatory in Puerto Rico in 2012. Embedded in a small, faint dwarf galaxy roughly 3 billion light-years away, sitting inside an unusually extreme magnetic environment that leaves a distinctive fingerprint on every burst that passes through it. Over the following decade, that single source produced thousands of individually detected bursts across multiple telescopes and frequency bands, an extraordinary output for an object originally assumed, like the Lorimer burst, to represent some singular catastrophic event. Arecibo itself is no longer standing, worth pausing on for a moment. Its enormous dish, suspended for decades over a natural sinkhole in the Puerto Rican jungle, ultimately failed structurally after a series of support cables snapped, and the instrument platform collapsed in December of 2020, ending the operational life of a telescope that had contributed, among a long list of other discoveries. This very first repeating fast radio burst, the pattern of repetition matters, scientifically, because it tells us something important, whatever produces these bursts. At least in the case of the repeaters, survives its own eruption. It isn't destroyed in a single cataclysmic event, the way, for instance, two neutron stars merging into each other would be. It bursts, recovers, and bursts again, sometimes within milliseconds of a previous burst, sometimes only after weeks of apparent quiet. That behavior is broadly consistent with a magnetar model, in which repeated starquakes or magnetic reconnection events can recur over the working lifetime of the star. But the sheer pace of repetition observed in the most active known sources pushes right up against the limits of what such a model can comfortably explain. One especially prolific repeater, first identified by the JWST telescope in 2022, was observed bursting at rates as high as 390 times per hour during its most active period. A single object in a galaxy some 400 million light-years away, contributing, all on its own and for a time, a measurable fraction of the estimated fast radio burst rate across the entire sky. Some analyses have gone as far as questioning whether the total magnetic energy stored in even an extreme magnetar's field is really sufficient to power that much cumulative radio output over the source's observed lifetime. An even sharper complication arrived in early when the JWST collaboration traced a newly identified repeating source back to its host environment and found something that did not fit the standard picture at all. The burst was not coming from a young star-forming galaxy, the kind of environment where massive stars are born, live briefly, and die as the supernova thought to leave magnetars behind. It was coming from the extreme outskirts of an old, massive elliptical galaxy, one where star formation had effectively ceased billions of years earlier, originating from a location roughly 130,000 light-years from that galaxy's center, in a region nearly devoid of stars altogether. Under the standard model, this should not happen. If fast radio bursts trace back to and magnetars are the direct remnants of core-collapse supernova from young, massive stars, then the bursts ought to cluster in young, actively star-forming galaxies, not in the quiet, ancient outskirts of a galaxy where the last supernova likely occurred billions of years before the burst was ever detected. One proposed resolution involves globular clusters, dense, ancient spherical groupings of old stars, where exotic close encounters between compact stellar remnants, colliding white dwarfs, merging neutron stars, are thought to occur far more frequently than in ordinary galactic environments, potentially producing a magnetar through a slow, delayed formation pathway entirely different from a direct supernova. If that explanation holds up under further scrutiny, it would mean the universe has more than one route to building the kind of object capable of producing a fast radio burst, and that the phenomenon isn't tied to any single formation channel, but can apparently arise from environments as different as the youngest, most active stellar nurseries and the oldest, quietest stellar graveyards in the observable universe. Woven into all of this is one more thread, arguably the most immediately useful scientific payoff to come out of fast radio burst research so far. And it has nothing to do with what produces the bursts, and everything to do with what they pass through on their way to us. Every fast radio burst, regardless of its ultimate source, functions as a kind of cosmic measuring tool because its dispersion, that delay between high and low frequencies discussed earlier, is a direct measurement of the total amount of ionized gas lying between its source and our telescopes. In 2020, a team led by the astronomer Jean-Pierre Marquardt used a set of fast radio bursts whose distances had been independently confirmed by locating their host galaxies to show that the relationship between burst distance and dispersion followed exactly what cosmology models of the intergalactic medium predicted. In doing so, the team effectively weighed the gas sitting in the vast, otherwise nearly undetectable spaces between galaxies, and confirmed that the total amount of ordinary matter in the universe matches what the standard cosmological model, built from the physics of the Big Bang and from precision measurements of the cosmic microwave background, had predicted all along. The confirmation closed a long-standing puzzle in its own right. For decades, astronomers had been able to directly observe, in stars, in galaxies, in hot intergalactic gas clouds, only about half of the ordinary matter that theory said ought to exist. The rest, dubbed the missing baryons, was assumed to be spread thinly through the space between galaxies, to diffuse and too cool to show up through any conventional method of detection. Fast radio bursts, passing directly through that same diffuse material on their way to Earth and picking up a measurable, quantifiable dispersion in the process, turned out to be exactly the tool needed to find it. A signal produced by a mechanism nobody fully understands, traveling through a medium that had never been directly measured before, ended up resolving a problem that had stood unresolved for 2 decades. The bursts themselves remain mysterious. What they revealed about the space between galaxies does not, and the bursts keep arriving. The CHIME telescope in British Columbia, an instrument with no moving parts at all. It's for long cylindrical reflectors simply lying still and letting the sky drift overhead each night, currently detects on the order of 2 to 3 fast radio bursts per day, and is in the process of being expanded with a network of smaller, outrigger stations designed to pin down burst locations with far greater precision than has previously been possible. The Square Kilometre Array, a next-generation radio observatory being constructed jointly across sites in Australia and South Africa, is being built with fast radio burst detection and localization as one of its explicit core objectives, at sensitivities and survey speeds well beyond anything currently operating. Every new instrument capable of watching the radio sky closely enough seems to find more bursts, and every new survey turns up sources that stretch the boundaries of what current models can comfortably explain. The catalogue grows. The exceptions accumulate at very nearly the same pace as the confirmations. Something out there, evidently in more than one kind of environment and by more than one possible route, is converting energy into some of the most extraordinary bursts of coherent radio light ever measured, doing it from regions smaller than a city, doing it from distances spanning most of the observable universe, and doing it, most days, entirely without anyone on Earth watching at the right moment to notice there is a kind of light older than any star, older than any galaxy, older, in fact, than atoms themselves in any form we would recognize today, and it happens to have been discovered by more or less the same accidental process as everything described so far, an instrument built for one purpose, stumbling onto something nobody had gone looking for in 1965. To radio astronomers at Bell Telephone Laboratories, Arno Penzias and Robert Wilson, working, as it happens, at the same institution where Carl Jansky had built his rotating antenna 3 decades earlier, were trying to use a large horn-shaped antenna in Holmdel, New Jersey. Originally built for early satellite communication work, to make precise measurements of faint radio sources, they kept picking up a persistent, low-level hiss of noise, coming evenly from every direction in the sky, that they simply could not get rid of. They checked the electronics. They checked for interference from nearby New York City. They found a pair of pigeons nesting inside the antenna, and suspecting their droppings might be responsible for the excess signal, cleaned the horn out thoroughly and evicted the birds. The noise remained exactly as strong and exactly as uniform as before what Penzias and Wilson had stumbled onto, without initially realizing it, was the faint afterglow of the early universe itself, the cosmic microwave background. Radiation released roughly 380,000 years after the Big Bang, At the moment, the young universe had finally cooled enough for electrons and protons to combine into stable atoms, allowing light to travel freely through space for the first time rather than being constantly scattered by a dense fog of charged particles. That light has been stretched by the ongoing expansion of the universe ever since, its wavelength lengthening over roughly 13.8 billion years until what began as visible light now arrives at Earth as microwave radiation with a temperature of just a little over 2.5 degrees above absolute zero, arriving with almost perfect uniformity from every direction in the sky, because it originated everywhere in the early universe simultaneously. Remarkably, a group of physicists at Princeton, led by Robert Dicke, had independently worked out from theoretical grounds that exactly this kind of relic radiation ought to exist, and had begun building their own detector specifically to search for it, unaware that a signal matching their prediction almost perfectly was already sitting, unexplained, in a colleague's data less than an hour's drive away. Once the two groups connected, the picture came together quickly, and the accidental discovery in Homdel was recognized for what it was: direct observational evidence of the Big Bang, arguably the single most important confirmation the theory has ever received. Penzias and Wilson shared the Nobel Prize in Physics for the discovery in 1978. In the decade since, 3 successive space missions, COBE, in the late 1980s and early 1990s, WMAP through the 2000s, and the European Planck satellite in the following decade, mapped that ancient light with steadily increasing precision, revealing that it is not, in fact, perfectly smooth after all. Tiny temperature variations, differing from the average by only about 1 part in 100,000, ripple across the whole sky, encoding the faint density fluctuations present in the infant universe, the gravitational seeds from which every galaxy, every cluster of galaxies, and every large-scale structure in the modern cosmos eventually grew. Those variations follow a very specific statistical pattern predicted by the standard cosmological model, a pattern so well measured by now that deviations from it stand out clearly against the noise. Which brings us to a patch of sky in the southern constellation Eridanus that does not follow that pattern. The region, spanning roughly 5 degrees, more than 10 times the apparent width of the full moon, first drew attention in the mid-2000s, when researchers analyzing WMAP data identified it as measurably colder than it ought to be, roughly 70 millionths of a degree Kelvin, below the sky's already frigid average temperature. Put in isolation, 70 millionths of a degree sounds trivial, and in most contexts it would be, but the cosmic microwave background is, by a wide margin, the most precisely measured radiation field in the history of physics, uniform across the sky to roughly 1 part in 100,000, and the ordinary hot and cold variations that do exist follow a well-defined statistical distribution. This particular cold region does not fit comfortably within that distribution. It is too large, too cold, and, according to the statistics, too improbable to be explained away as an unremarkable random fluctuation. Researchers have placed the odds of encountering a deviation this extreme, by chance alone, in a universe that genuinely matches the standard model, at under 2%. Multiple explanations have been proposed over the years since. The leading conventional candidate involves a supervoid, an enormous, unusually empty region in the large-scale structure of the universe, lying directly along our line of sight toward the cold spot. As the ancient light of the cosmic microwave background passes through such a void on its way to us, it loses a small amount of energy through a subtle process called the integrated Sachs-Wolf effect, related to the way the accelerating expansion of the universe very slightly reshapes the gravitational terrain that the light is traveling through. Follow-up work using the Dark Energy Survey, did confirm the existence of a genuine supervoid in almost exactly the right direction. An underdensed region roughly 1 billion light-years across, one of the largest such voids ever mapped. But when researchers worked through the detailed calculations, the supervoid on its own turned out to account for only part of the missing temperature, not all of it. A gap remained. More recent work, published in 2023 and 2024, has proposed a different, complementary explanation. Researchers identified a statistically meaningful correlation between the positions of nearby spiral galaxies and patches of unusually cold sky within the cosmic microwave background data more broadly, hinting at a previously unaccounted for foreground effect, essentially a systematic dimming or cooling imprinted on the ancient light by relatively nearby galactic structures that happen to sit along the line of sight, contaminating what researchers had been treating as a pristine signal from the early universe. The Eridanus supergroup, an unusually large concentration of spiral-rich galaxy groups relatively close to us in cosmic terms, happens to sit almost precisely within the boundaries of the cold spot region. If that foreground effect turns out to be real and significant, it would mean that at least part of what has been read for 2 decades as an anomaly from the birth of the universe is instead a much more recent signal generated by structures far closer to home, layered on top of and partially obscuring the genuinely ancient light beneath it. In effect, astronomers may have spent years mistaking a nearby whisper for evidence of something unusual in the primordial shout. The honest state of the science at the moment is that neither explanation on its own closes the case, and it is entirely possible that some combination of the two, an underlying supervoid plus a layer of foreground contamination from the galaxies sitting along the same line of sight, will eventually account for the full anomaly once the data and the models are refined further. What is not in dispute is that the cold spot itself is real, a genuine, statistically significant, still only partially explained cool patch sitting in the oldest light human instruments have ever managed to detect. First flagged more than 2 decades ago and still, as of the most recent published analyses, an open item on the list of things the standard cosmological model has not fully accounted for. It is worth sitting with the strangeness of that for a moment. The light itself is essentially the oldest thing it is possible to observe directly, older than any galaxy, any star, any planet, and somewhere within that ancient light, spread across a patch of sky roughly 10 full moons wide, sits a genuine discrepancy that 2 decades of careful, internationally coordinated research still hasn't fully resolved. Not because nobody has looked closely enough, because the anomaly appears to sit at the intersection of 2 different explanations. An ancient void and a nearby cluster of galaxies, both real, both measurable, and not yet cleanly separated from one another in the data. And there is one more entry left in this particular catalogue, arguably the strangest of them all, because unlike the others, it does not merely defy easy explanation. It defies a boundary that astronomers had, until fairly recently, considered one of the more dependable rules in all of pulsar physics. Recall, from a little earlier, the idea of the pulsar death line, the boundary in the physics of a spinning neutron star below which its combination of rotation speed and magnetic field strength should no longer be able to power the particle cascade responsible for a radio beam. Cross that line, slow down enough, and a pulsar is supposed to fall silent, its lighthouse beams switched off for good. Still spinning, still magnetized, but no longer broadcasting. That prediction held up reasonably well for decades. Then, starting in the early 2020s, a series of objects turned up that appeared to be doing exactly what the deathline said should be impossible. The first came from the Murchison Wide Field Array, the low-frequency companion instrument to ask, sitting in that same radio-quiet stretch of Western Australian desert. Researchers, led by the astronomer Natasha Hurley-Walker at Curtin University, working through archival data collected between January and March of 2018, found a source initially spotted by an undergraduate student on the team named Tyrone O'Darty that pulsed on and off with a period of roughly 18 minutes, remaining bright for somewhere between 30 seconds and a minute during each cycle. The result, published in Nature in early described a source roughly 4,000 light-years away, emitting strongly polarized, highly structured radio pulses at an interval more than 1,000 times longer than the rotation period of the slowest, previously known radio-emitting neutron star. If the object really was a spinning neutron star, its rotation rate placed it not just beyond the death line but dramatically, almost absurdly far beyond it, deep into territory where the standard particle cascade mechanism responsible for pulsar radio emission has no obvious way to keep functioning at all. Two broad explanations emerged quickly, and both remain seriously considered. One holds that the object is an extraordinarily unusual kind of neutron star, sometimes described as an ultra-long period its rotation having been dramatically slowed, far more than ordinary pulsar spin-down alone would predict, potentially through interaction with a surrounding disk of leftover material from its formation, a mechanism that could in principle push a young neutron star's rotation period out to unusually long values relatively quickly. The other holds that the object isn't a neutron star at all, but instead a highly magnetized white dwarf, the compact remnant left behind by a sun-like star rather than a massive one, spinning at a rate that would be entirely unremarkable for a white dwarf even though it would be extraordinary for a neutron star. Its magnetic field strong enough to generate a pulsar-like beam through a broadly similar, though less extreme, physical mechanism. Both explanations require stretching some part of well-established stellar physics into unfamiliar territory. Neither has been ruled out the following year. 2023 brought a second and even stranger example, again from the Murchison Wide Field Array, this time in collaboration with additional facilities, an object designated by its sky coordinates, showing pulses at intervals of 21 minutes and 58 seconds, each individual pulse lasting anywhere from about 30 seconds up to 5 minutes. What made this source especially remarkable was not just its period, but its persistence. Researchers traced its behavior backward through decades of archival radio data from multiple older instruments and found the same 22-minute rhythm present as far back as 1980, meaning the object had been pulsing reliably on almost exactly the same schedule for at least 35 years, its period unchanged to within a small fraction of a second over that entire span. Located roughly 15,000 light-years away in the constellation Scuti, and showing polarization properties that strongly suggest, though do not conclusively prove, a neutron star origin. This source sits so far below the theoretical death line that a neutron star spinning that slowly should, according to the standard model, have no meaningful way of generating a coherent radio beam at all. And yet it had apparently been doing exactly that, with remarkable stability, for at least 3.5 decades before anyone noticed. The community working on these objects remains genuinely divided, and it's worth being honest about that rather than picking a side the evidence doesn't yet support. No single proposed explanation accounts cleanly for every observed property of every one of these sources simultaneously. Some show polarization patterns that favor a neutron star interpretation. Some show emission behavior that fits more comfortably with a white dwarf. And in the years immediately following these first two discoveries, the population of known long-period radio transients kept growing, each new member adding another data point without settling the underlying disagreement. One object identified through ASCAP itself, reported in 2024, pulses with a period of roughly 54 minutes and shows something not previously documented in any of its slower pulsing relatives. 3 distinct emission states, cycling between intervals of bright, structured pulses, intervals of much weaker and less organized emission, and stretches of apparent complete silence. A behavioral complexity that any successful model of these objects will eventually need to explain in full. And an even more extreme example, also found through ASCAP and reported not long afterward, pushed a known range of these periods dramatically further out. A source pulsing with an interval of roughly 6.5 hours. By a wide margin, the longest period yet recorded for an object of this kind. So far removed from anything resembling ordinary pulsar behavior that some researchers have begun asking whether long-period transient is even the right conceptual category for it, or whether objects at this extreme end of the range might be something else again, perhaps part of a binary system rather than a single, isolated star, with the observed periodicity reflecting an orbit rather than a spin. The most recent published analyses, from within the last several months, as of this telling, have begun exploring exactly that possibility for at least one of these very long period sources, tentatively suggesting an orbital period in the neighborhood of several hours might better explain the data than pure rotation. Though this remains preliminary and is very much still being worked out taken together, these objects, now numbering somewhere in the dozens, spanning periods from about 18 minutes out past 6 hours, form a genuinely new category of astronomical source, discovered essentially by accident. Through archival data nobody had originally collected with these objects in mind, using instruments built primarily for entirely different survey goals. They share a family resemblance: long, highly regular pulsing intervals, strong polarization, a location, in most cases, consistent with our own galaxy rather than anywhere more distant, and a fundamental, unresolved disagreement among researchers about what kind of object or objects could possibly be producing them. Some may turn out to be exotic neutron stars, driven into unusually slow rotation by mechanisms not yet fully worked out. Some may turn out to be magnetic white dwarfs, a class of object whose pulsar-like behavior had barely been considered seriously before these discoveries forced the issue. Some, at the longest end of the observed range, may turn out not to be single spinning objects at all, but binary systems whose orbital motion, rather than any star's own rotation, sets the rhythm we detect from Earth. It is entirely possible that more than one of these explanations is correct simultaneously, describing genuinely different populations of objects that happen, for now, to be lumped together under a single observational label simply because nobody has yet worked out how to reliably tell them apart. What is not in question is that these signals were there long before anyone found them. The archival data that revealed the first 2 objects had been sitting, unexamined in this particular way, for years before anyone thought to search it specifically for slow, regular pulses, rather than the much faster rhythms every previous pulsar search had been built to find. The 35 years of quiet, consistent pulsing, traced backward through decades of old recordings, makes that point about as clearly as it can be made. The signal was arriving the entire time. The search simply hadn't been built yet to notice it. It's worth taking a step back now, away from the details of any single signal, to look at the shape formed by all of them together. Odd radio circles were not new in 2019. They had, in all likelihood, been sitting in the radio sky for billions of years, the visible aftermath of something violent that happened in a handful of distant galaxies, long before our own sun had finished forming, waiting for an instrument sensitive enough to faint, diffuse structures to come along and noticed them. Jaminga was not new in 1972, or 1991, or 2019. It had been broadcasting gamma rays, then radio waves at a frequency nobody thought to check, then a halo of antimatter and high-energy gamma radiation, for roughly 300,000 years before any of those signals were actually received and understood by anyone. Fast radio bursts were not new in 2007. Whatever produces them, magnetars or something else entirely, has apparently been doing so for as long as the relevant class of object has existed, at an estimated rate of somewhere around 1,000 or more bursts a day across the whole sky, almost all of them unnoticed, because no telescope happened to be pointed at the right patch of sky at the right instant. The cold spot has been sitting in the oldest light in the universe since that light was released, 380,000 years after the Big Bang, and the long period transients, by the clearest evidence available, the 35 years of consistent pulsing traced back through old archival recordings, had been pulsing away entirely unnoticed for decades, before anyone built a search capable of catching a rhythm that slow. None of these are new phenomena. They are old phenomena, newly perceived, and that particular pattern, a discovery revealing not a new event but an old one we simply lacked the means to detect, is not unique to radio astronomy. It shows up with almost startling regularity every time astronomers open a genuinely new window onto the sky. Consider X-ray. Earth's atmosphere is opaque to them, which means that, unlike radio waves, X-ray astronomy could not even begin until instruments could be lifted above the atmosphere entirely. That happened first with a series of sounding rockets in the years following the Second World War, brief flights lasting only minutes before falling back to Earth. And it was one such flight, in 1962, led by the physicist Riccardo Giacconi, that made the first confirmed detection of an X-ray source beyond our own solar system, a compact, extraordinarily bright object in the constellation Scorpius, now known as Scorpius X1, which turned out to be a neutron star locked in a close binary orbit with an ordinary star, pulling material from its companion and heating that material to X-ray emitting temperatures in the process. That single rocket flight, a few minutes of data collected almost by chance while the instrument was technically searching for something else, opened up an entire new field, one that would go on to reveal neutron stars, black holes, and the hot X-ray glowing gas that fills entire clusters of galaxies, all of it invisible to any telescope confined to visible light, all of it apparently sitting there in plain sight the whole time, simply beyond the reach of any instrument built before the rocket and later the satellite. Made it accessible. Gamma ray astronomy tells an even stranger version of the same story. In the late 1960s, the United States launched a series of satellites called Vela, built not for astrophysics at all, but for a strictly military purpose, monitoring compliance with the Nuclear Test Ban Treaty by watching for the distinctive gamma-ray signature of a nuclear detonation, whether on Earth or in space. Instead, the Vela satellites began registering brief, powerful bursts of gamma radiation arriving from directions that had nothing to do with Earth at all, clearly originating from deep space rather than from any weapons test. It took researchers years of careful analysis, checking and rechecking the data, before the results were released publicly in 1973, revealing what came to be known as gamma-ray bursts, now understood to be among the most energetic explosions in the universe, associated with the collapse of massive stars or the violent merger of compact stellar remnants. A defense satellite, built to watch for one very specific and very human kind of explosion, ended up discovering an entirely different, far more powerful class of explosion happening across the universe, purely as an unplanned side effect of doing its actual job. Gravitational waves followed a similar arc, if on a much longer timescale, Einstein's general theory of relativity predicted their existence in 1916. Ripples in the fabric of space-time itself, generated whenever massive objects accelerate violently enough, spreading outward at the speed of light and, in principle, very slightly stretching and compressing everything they pass through along the way. For the better part of a century, that prediction remained purely theoretical, because the effect was expected to be almost unimaginably small, a distortion measured in fractions of the width of a single proton, far below what any instrument then existing could hope to detect. It took the construction of LIGO, a pair of laser interferometers, each with arms several kilometers long, engineered to detect exactly that kind of vanishingly small distortion, before the first direct detection finally came on the 14th of September, 2015, a signal produced by two black holes, each dozens of times the mass of our Sun, spiraling together and merging into one roughly 1.25 billion light-years away, an event whose gravitational ripples had been traveling toward Earth for well over 1 billion years before an instrument sensitive enough to register them was finally switched on. Astrophysical black hole mergers, it turned out, had been happening regularly throughout the history of the universe. We had simply never had a way to hear them until that moment. Neutrino astronomy completes the set in its own way. Neutrinos are produced by some of the most energetic processes in the cosmos, but they interact with ordinary matter so weakly that trillions of them pass through every square centimeter of the Earth's surface every second without disturbing a single atom along the way, which makes them almost impossibly difficult to detect directly, and just as difficult to trace back to a specific astrophysical source. It took an instrument on the scale of a full cubic kilometer, a lattice of light-sensitive detectors buried deep in the ice at the South Pole and known as ice, before astronomers finally managed, in 2017, to trace a single high-energy neutrino back to a specific point of origin, a blazar, a supermassive black hole actively feeding and blasting a jet of particles almost directly toward Earth, roughly 4 billion light-years away. Here again, the same underlying story, a category of cosmic messenger that had been arriving at Earth constantly for the entire history of the planet, simply waiting for an instrument large and sensitive enough to finally catch one and trace it home. Put all of that alongside the radio astronomy signals covered earlier, and a pattern starts to come into focus that goes beyond any single discovery. Every genuinely new instrument, tuned to a wavelength or a particle or a phenomenon that no previous instrument could access, has revealed activity that was already happening, often for a very long time, entirely unnoticed. That is, in one sense, simply how observational science is supposed to work. Better tools reveal more of reality. That's the whole point of building them. What is a little more unusual and worth sitting with honestly rather than smoothing over is the ratio involved. In earlier eras of astronomical discovery, the 1950s and 60s, when radio astronomy first revealed quasars, pulsars, and the cosmic microwave background itself, the 1990s and 2000s, when X-ray and gamma-ray observatories revealed magnetars and confirmed the accelerating expansion of the universe. Each of those genuinely surprising discoveries was, within a matter of years, or at most a couple of decades, folded into an expanded version of the standard theoretical framework. The questions got answered. The model grew to accommodate the new phenomena, and the field moved on to the next set of open questions. The signals gathered here have not, for the most part, followed that same trajectory, at least not yet. Odd radio circles, first identified in 2019, remain without a settled explanation. Fast radio bursts, discovered in 2007, are still debated after nearly 2 decades of dedicated research involving hundreds of scientific teams. The cold spot, flagged in the mid-2000s, remains only partially accounted for after 20 years of increasingly precise follow-up observation. The long-period radio transients, first identified in 2022 and 2023, still lack any settled consensus on what kind of object is actually responsible for them. None of these are failures of effort or of instrumentation. If anything, they represent some of the most heavily resourced, most carefully studied problems in contemporary astrophysics. They simply haven't resolved on the timescale that earlier generations of anomalies typically did. And meanwhile, new instruments coming online in the years immediately ahead. An expanded square-kilometer array, more sensitive gravitational wave detectors, a new generation of cosmic microwave background experiments, generally referred to as CMBs, 4, and the newly operational Vera C. Rubin Observatory in Chile, surveying the entire visible sky roughly every few nights at a depth and cadence no previous facility has matched, are all but certain if the pattern holds. To add still more items to this list rather than subtract from it, that is not, in itself, a cause for alarm. It is, if anything, a fairly ordinary description of what it looks like to be in the middle of expanding a picture rather than at the end of completing one. But it is a genuinely different position than the one astronomy occupied for much of the 20th century, when new discoveries tended to arrive at a pace theory could reasonably keep up with. Right now, across several independent, well-funded areas of observational astrophysics simultaneously, the rate of new unexplained phenomena appears to be outpacing the rate at which theoretical models are managing to absorb them. Whether that gap narrows again over the coming decade, the way it has after previous bursts of discovery, or whether it continues to widen for a while yet, is itself an open and genuinely interesting question. One that nobody currently has a confident answer to. There is one more category of signal worth considering before closing, because it sits underneath a much older and more familiar question, one that has quietly shaped the framing of nearly every signal discussed so far. Whether or not it was stated outright, are we alone the organized search for signals from other civilizations is, by the standards of everything discussed so far, a genuinely old undertaking dating back to 1960, when the astronomer Frank Drake used the Green Bank Radio Telescope in West Virginia to point briefly at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, listening near the frequency emitted naturally by neutral hydrogen gas, on the reasoning that any civilization familiar with basic physics would likely recognize that particular frequency as a sensible, universal channel to transmit on or listen to. Drake called the project Ozma after the princess of a fictional, more advanced land in a children's book series, and while it detected nothing, it established the basic template that radio-based searches for extraterrestrial intelligence have followed ever since. The following year, at a small conference held at the same observatory, Drake introduced a way of organizing the problem that has since become famous well beyond the field itself. A simple equation multiplying together a chain of factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, the fraction of that life that develops intelligence and technology, and so on, down to the average length of time a technological civilization might be detectable before it either destroys itself or simply falls quiet. The equation was never intended as a tool for producing a confident numerical answer. Several of its terms remain entirely unknown even now. Its real value was, and still is, as a framework for thinking clearly about exactly which unknowns are actually driving the uncertainty in the question of whether we are alone. The most famous single event in the history of that search came 17 years later, on the 15th of August, 1970, at the Big Ear Radio Telescope on the campus of Ohio Wesleyan University in Delaware, Ohio. Big Ear was not a steerable dish. It observed by letting the rotation of the Earth carry a fixed patch of sky slowly across its stationary field of view. And on that particular night, its receiver, tuned near the same neutral hydrogen frequency Drake had chosen for Project Ozma 17 years earlier, registered an intensely strong, narrowband signal rising and falling over about 72 seconds, arriving from the general direction of the constellation Sagittarius, its strength and shape closely matching what would be expected from a genuine, fixed celestial source sweeping through the telescope's beam. Several days later, a volunteer astronomer named Jerry Emin, reviewing the printed data by hand, spotted the sequence of numbers and letters representing the signal's rising and falling intensity, circled it in red pen, and wrote a single word in the margin beside it. Wow. The signal has never been detected again, despite repeated, dedicated follow-up searches of the same patch of sky using telescopes, considerably more sensitive than Big Ear, nearly 5 decades on. The WOW signal remains formally unexplained, though not for lack of proposed candidates. Various researchers have suggested it might have originated from a passing comet venting hydrogen gas, an explanation that gained some traction when comets were later found to pass near the right part of the sky, though the timing and details have never lined up cleanly enough to be fully convincing. More recent analyses, published within just the last couple of years, have proposed that the signal might be explained by a rare, naturally occurring flare from a small, cold cloud of interstellar hydrogen gas, a genuine astrophysical event rather than any kind of transmission. And a separate reanalysis of the original archival data has recently refined the signal's likely position and properties, narrowing, though not yet closing, the search for its true origin. None of these explanations has achieved anything close to consensus. The honest summary remains what it has been for most of the last 50 years. Something real and strong swept across a radio telescope's beam for just over a minute one night in 1977, and nobody has yet identified with real confidence exactly what it was. The modern successor to that early era of listening is a project called Breakthrough Listen, a decade-plus initiative using some of the world's most capable radio telescopes to conduct by far the most sensitive and systematic search for artificial signals ever attempted. Its most talked about result to date came from an observation of Proxima Centauri, the nearest star to our own Sun, conducted using the Parkes telescope in Australia, the same instrument responsible for both the original Lorimer burst and its follow-up confirmations described earlier. Over several days in the spring of 2019, the telescope recorded a narrowband signal that, when a summer research intern re-examined the archived data more than a year later, in the autumn of 2020, passed every one of the project's standard filters for identifying a plausible technosignature. It appeared only when the telescope was pointed directly at Proxima Centauri, not when it was pointed slightly away. It persisted for more than 2 hours, and its frequency appeared to drift in a manner broadly consistent with the kind of Doppler shift expected from a transmitter located somewhere within that star system. The signal, informally designated Breakthrough Listen Candidate 1, became, for a period of intense scrutiny, the single most compelling candidate technosignature the modern SETI community had ever produced. Extensive follow-up analysis, published a little over a year later, ultimately traced the signal's most likely origin to something considerably less dramatic, a specific, unusual, but ultimately terrestrial form of radio frequency interference, most likely generated by the intermodulation of signals from ordinary electronic devices somewhere in the vicinity of the telescope, whose combined output happened to mimic, closely enough to pass initial screening, The profile researchers had defined for a genuine technosignature. The exact device responsible was never conclusively identified, but researchers found numerous other examples of very similar interference at closely related frequencies tied to common electronic oscillators scattered elsewhere throughout the observatory's archived data. It was not, in the end, a signal from Proxima Centauri, but it did serve a genuinely useful purpose for the field, demonstrating in fine detail exactly how difficult it can be to distinguish a truly compelling candidate technosignature from an unusually well-disguised piece of ordinary human technology, and prompting real improvements in how the project screens and verifies future candidates. It's worth placing that history alongside everything discussed earlier in this account, because the two threads connect in an interesting way. The absence of any confirmed detection across more than 6 decades of searching sits at the heart of what's commonly called the Fermi paradox, the observation, generally attributed to the physicist Enrico Fermi in an offhand lunchtime remark, that if intelligent, technological civilizations are at all common in a galaxy as old and as vast as ours, we would reasonably expect to have detected some sign of at least one of them by now, and the fact that we apparently haven't seems, on its face, to call that assumption into question. But look again at everything covered in the earlier parts of this account. Odd radio circles among the largest individual structures ever identified in the observable universe went completely undetected until 2019, not because nobody was looking, but because no previous instrument had been sensitive enough to faint, extended radio structures to notice them. The full extent of Geminga's antimatter halo, an object bright enough in gamma rays to be one of the most prominent sources in the entire sky at that wavelength, wasn't properly mapped until 2019 either, despite the source itself having been catalogued, in a partial and confusing way, since 1972. Fast radio bursts, now understood to occur at a rate of something like 1,000 or more times a day across the whole sky, went entirely unnoticed until 2007, and even then very nearly got dismissed as microvivant interference before their reality was confirmed. The long-period radio transients had, by the clearest available evidence, been pulsing steadily for at least 35 years before anyone built a search capable of noticing a rhythm that slow. In every one of these cases, an entire category of loud, energetic, naturally occurring phenomenon sat completely undetected for years or decades, not because it wasn't there, but because the search being conducted, however careful and well-intentioned, simply wasn't built to catch it. None of that is an argument that extraterrestrial intelligence exists, and it shouldn't be read as one. It's a considerably more modest and, in its own way, more interesting point, given how much loud, natural, unambiguously real activity in our own galactic neighborhood went completely undetected by decades of careful astronomical searching, simply because the instruments involved happened to be tuned to the wrong frequency, the wrong sensitivity, or the wrong moment. It becomes genuinely difficult to place a great deal of confidence in the idea that 60-some years of comparatively narrow, comparatively low-powered searching for artificial signals has meaningfully ruled out their existence. The absence of a confirmed detection, in other words, may say considerably less about what is or isn't out there than it says about how limited our searches have been so far, and continue to be even now. That is not a case for optimism, and it is equally not a case for pessimism. It's simply an argument for a certain amount of humility about how much any current silence can actually tell us, alongside a reasonable expectation that the instruments coming online over the next decade, considerably more sensitive and considerably more comprehensive than anything used before them, will have a genuinely better chance of settling the question than anything that came before its probably worth gathering together, plainly and without much embellishment. Exactly what is and isn't settled across everything covered here, because the honest answer is a mix. And pretending otherwise wouldn't serve the story well. The odd radio circles are confirmed. Real, physically consistent structures, observed independently by multiple telescopes at multiple frequencies. What remains open is their cause, whether they trace back to merging supermassive black holes, to the aftermath of an intense burst of star formation, to a jet-viewed end-on, or to some combination or alternative not yet seriously proposed. Geminga's identity as a pulsar and the broad outline of its antimatter halo are now well established. What remains less certain is the precise proportion of the galaxy's total positron excess that pulsars like it can account for, and whether some smaller residual contribution might still be explained by something else entirely. Fast radio bursts are confirmed as real, extragalactic, and almost certainly connected to magnetars, in at least some cases, thanks to the 2020 galactic event. What remains unresolved is whether magnetars alone, in some more extreme form than any yet observed nearby, can account for the full range of burst energies and repetition rates recorded so far, or whether more than one physical mechanism is contributing to what has, until now, been treated as a single, unified phenomenon. The cold spot is a confirmed statistical anomaly in the cosmic microwave background. What remains unsettled is how much of it traces back to a genuine, large-scale void, how much to nearby foreground contamination, and whether those two explanations, once properly combined, will turn out to account for the whole deficit or still leave something over. And the long-period radio transients are confirmed, growing steadily in number, and confirmed to violate the traditional pulsar deathline in some form. What remains entirely open is the basic question of what kind of object or objects is actually responsible, a question that current data has not yet been able to answer with confidence. None of that is a small list, and none of it looks likely to be fully settled particularly soon. But there is real reason to expect meaningful progress within the coming decade, because the instruments arriving over that period are, in nearly every case, built specifically with sensitivities that should help address exactly these questions. The square-kilometre array, under construction across sites in Australia and South Africa, will eventually operate at a survey speed and sensitivity well beyond ASCAP or the Murchison Wide Field Array, the two instruments responsible for most of the discoveries described in this account, meaning it should be able to both find new examples of these phenomena far more quickly and study known examples in far greater detail than has been possible so far. The Vera C. Rubin Observatory in Chile, now in the early years of its planned decade-long survey of the entire visible southern sky, repeating that survey every few nights, is built primarily to study visible light rather than radio waves, but its ability to catch fast-changing events as they happen, rather than after the fact in archival data, may prove useful for tracking down optical counterparts to some of these radio phenomena, something that has proven difficult so far for nearly all of them. A next-generation cosmic microwave background experiment, generally referred to by the shorthand CMBs for, is being planned specifically to map the ancient light of the early universe with several times the precision of the Planck satellite, which should help settle, one way or another, how much of the cold spot's temperature deficit is primordial and how much is foreground contamination, and proposed next-generation gravitational wave observatories, considerably larger and more sensitive than the current LIGO and Virgo detectors, are in active planning stages, promising to extend that particular sense considerably further out into the universe than is currently possible. None of this guarantees quick answers. Odd radio circles were first identified in 2019 and remain unexplained 6 years on. Fast radio bursts have been studied intensively for nearly 2 decades without full resolution. There is no particular reason to expect any of the remaining open questions to resolve neatly on any predictable schedule. What does seem reasonably likely, based on the pattern traced through this whole account, is that each new instrument, each new leap in sensitivity, will keep doing what every previous leap in sensitivity has done, revealing activity that was already there, quietly waiting that in the end might be the most durable thing to take away from all of this. Not a specific answer, because in most of these cases there isn't one yet, but a broader sense of scale. A little under a century ago, a Bell Labs engineer trying to solve a mundane problem with transatlantic telephone static built a rotating antenna out of parts, including a car's old wheels, and discovered, entirely by accident, that our own galaxy was broadcasting in radio waves. Every discovery that followed from that moment, the pulsars, the cosmic microwave background, the odd radio circles, Geminger's antimatter halo, the fast radio bursts, the long-period transients, has been some version of the same basic realization, arrived at again and again by different people with different instruments. At different times, the universe was never quiet. It was simply broadcasting on channels we hadn't yet learned to receive. Back in the desert, the dishes are still turning, slowly, tracking the same patch of sky they were pointed at earlier in this account. Somewhere in the data streaming off them tonight, recorded and archived and waiting. There is very likely something nobody has looked at closely enough yet to notice. A shape that doesn't match the catalogue. A rhythm too slow for any existing search to flag. A burst too brief for any current algorithm to catch. It will most likely sit there for a while. The way the odd radio circles sat in old Indian archival data for 6 years. The way the first fast radio burst sat in Parkes data for 6 years. The way that 22-minute pulsing source's rhythm sat quietly in decades of old recordings before anyone thought to look for something pulsing quite that slowly. Eventually, in all likelihood, someone will look and notice, and write 2 letters and a question mark, or something like it. In the margin, the universe has been broadcasting for as long as there has been a universe to broadcast in. We only started listening a little under 100 years ago, and even now, we've only really learned to listen on a handful of channels out of everything there is to hear. That's not a reason for urgency, and it isn't a cause for alarm. It's simply where things stand tonight, in a quiet stretch of Australian desert, and in radio-quiet valleys and mountaintops and orbiting satellites scattered elsewhere around the planet, all of them still listening, patiently, for whatever comes next.